Yeah, good morning, everyone. Welcome to another TRR seminar. It's maybe the first after the summer break. So today we have Michael Cox from University of Edinburgh is doing a PhD there with Jack Boussinesq and Hussein Kafiapar. He's here, and before his PhD, he was in Birmingham in the university to do his master degree in theoretical physics on quantum mechanics. And so he's in Hamburg for a 2-month research visit, and he will be working. Okay, in Michael's words, he's working primarily with pen and paper to study the interaction of waves and vortices in atmosphere and ocean. And this is what we will hear about today, right?
Yes, yeah.
Okay, so go ahead.
Okay, thanks. Thanks for having me. So it's a slightly shorter talk title than was advertised. So I'm mostly going to be talking about the inertia-gravity-wave diffusion, by the geostrophic flow, and the impact of flow time dependence in this process. So this is work with Hussein and Jack. Hussein's now in Durham, but Jack's still at Edinburgh. It's got nothing to do with clouds, but as oceanographers, you'll appreciate that black text doesn't show up very well against the ocean. That's why there's clouds in the background. Oh, there we go. So I'm going to start talking about the Wigner transform, which is being included by special request. So most of the talk won't be related to that, but there's a few slides on it because it motivates. Well, it's used to go from your fluids equation of motions to equations for wave action evolution, which is related to what I'll talk to later, but not most of what I'll talk about. Then I'll talk to you about the inertia-gravity-wave diffusion and our in the initial derivation of this diffusion process, there's an assumption that the flow is moving so slowly that it's time independent. And this is something that I'll relax for the rest of the talk and show you that it's a well-justified assumption. And then I probably won't get time to talk about generalizing this diffusion process to other flow-induced perturbations, but if anyone wants to talk about it afterwards, yeah, I've got some slides on it as well. So what is the Wigner transform? Full transparency, I'm not entirely sure, but I'll do my best to explain it. So it takes a field, phi, so this can be a scalar field or a vector field. In our case, phi is a vector field of your flow velocity, so uv and w, and buoyancy. And it transforms it in a similar way to a Fourier transform, but it's local. So you can sort of see this from the expression at the top of your screen. You are looking at the Wigner transform. I'm going to try and use the, here we go. So you're looking at the Wigner transform at a point x, and this integral goes from before x and after x in y. So it's like a local Fourier transform. That's the main difference between the two approaches. So what's the advantage of this? Well, because of the local nature, it doesn't rely on things like the WKB approximation, so spatial scale separation. If you were doing classical methods like just a Fourier transform of your equations of motion, you have to make some sort of assumptions on the scale separations, on spatial homogeneity, I think as I understand it. With the Wigner transform, you don't have to do this. It captures the different scales without making those assumptions. So yeah, actually, one thing I should say, so this K here, it's essentially your, it's essentially like a local wave number. So if you had, say, a packet here, this packet has a position in space X, but then the waves inside the packet have a wave number that they are propagating with. So that's how it enables us to have both a position and a wave vector, whereas usually we'd be used to working with one or the other. So yeah, the key takeaway is it captures the characteristics of different wave packets at different points in space without having to average or sum their various properties. And because of this localization, it can deal with things like changing parameters in the system. So if you have the Boussinesq equations and you're concerned with variable buoyancy flows, so your buoyancy frequency n is varying, if you were to Fourier transform, I don't think you'd be able to deal with this very well. Whereas if you take a Wigner transform, you can take into account that your buoyancy frequency n is varying with, say, depth. So yeah, that's one advantage. And actually that's what I'm doing here is I'm working with internal tides interacting with the geostrophic flow. And because the internal tides are over a scale where n is varying quite a lot, you don't want to keep n constant. And also because the internal tides are of a similar scale to the flow, you don't have the scale separation that you would in other situations. So that's why the Wigner transform is a real plus in this case. So this just demonstrates this. If you take the Fourier transform over this domain versus the Fourier transform over all these subdomains, you get two different answers if you've got different scales going along. But the Wigner transform of the entire domain preserves more dynamics and preserves the different like wavelengths of different packets in different parts of the domain. So this is a summary of basically Miles Savas' thesis, who was my predecessor, and how he, Jacques, and Hussein have used the Wigner transform to get to a scattering equation for wave action and a diffusion equation for wave action. I should have said actually, so this isn't a technique that they've pioneered. This was first introduced in quantum mechanics, and I think in the context of the fluid equations, this paper by Rizek is the first one that used it in this way. So the work that Jacques and Miles have done is based on that. So our starting point is the equations in motion. So this could be your Boussinesq equations, your shallow water equations. And you can apply the Wigner transform to any equations of motion. You just might not get anything meaningful, but in this case they do. So you apply the Wigner transform to the equations of motion. And once you have the Wigner transform of these equations, you can use timescale separation and an assumption of weak flow to expand that using a perturbation expansion. And that gives you the scattering equation here. So the left-hand side is just like a wave action conservation, and the right-hand side is your scattering term. I'm going to talk a bit more about the diffusion equation and what all these symbols mean later. So don't worry too much about the details now. But the important thing here is that to go from your equation of motion to the scattering equation here, we haven't had to assume spatial scale separation. Whereas if you're taking like the Fourier transform, I think you would have to assume some sort of homogeneity there, which would be not as advantageous. So
are you sure that in this lower scattering equation, the propagation in phase space is there?
No.
Zauber, it's not there.
This term, no? Yeah. Yeah. Or no?
It's not there. So.
How do you mean? I mean, you've got.
Well, it's the same as the action conservation equation on the upper right.
But there's propagation in phase space in the action conservation equation.
Yeah, the upper right, but not the lower left. I think that's replaced by this S term.
No, you've got this term here, which is a gradient of.
The new equation, but not the others.
Not entirely. I think that's then okay. So I'm sorry, I must have.
Otherwise, it would be completely identical except for the right hand side.
Yeah, I think maybe maybe these omegas are different here. I'll need to double check that. Sorry, but I think the propagation in K space is captured in the scattering term as well, because. Yeah, you can take a limit of this, which gives you the diffusion equation, which definitely has propagation. I'll go back and check that for you. So don't trust these equations. But you do have a scattering equation that has variation in both physical and wave vector space. So all of that's summarized in this paper here by Miles on scattering. So if you want to see the proper version of that equation, go to that paper. And I'll be working with tides where you have variable buoyancy frequency. Miles and Jacques have already done it with constant buoyancy frequency. So in the case of your baroclinic mode, is that right?
would be very.
Okay, yeah, so in the baroclinic case, whereas I'm working with the barotropic case, I think I always go.
No, the other way around.
The other way around. Okay, the other way around. But it's already been done for the other case. And actually, if you want an introduction to the Wigner transform, which is less mathsy than number 2, is probably a more accessible paper. And the best introduction, I'd say, is Miles's thesis, which introduces the concepts more clearly. So, yeah, I'm going to be working while I'm here on this side of things, deriving from the from the linearized hydrostatic Boussinesq equations, a scattering equation for internal tides, and then hopefully we'll be able to do some ray tracing with that and make some predictions, which we can compare to the sort of work that Carsten and Manita have been doing with tidal beams going into wave eddies already. So that's the Wigner transform. You can also go from the equations of motion on your left here and assume space and time separation. And that gets you the action conservation equation. Now, one thing Jacques wanted me to point out is the traditional way of deriving the action conservation equation involves the ray equations. So you have to consider a single wave packet with a single K. The Wigner transform you can actually apply to the equations of motion here to get the action conservation equation without having to keep your wave vector constant. So it's a cleaner way of deriving the action conservation equation from the equations of motion than the traditional methods. Yeah, so you can get the action conservation equation from space and timescale separation. And then if you make a weak flow assumption, you get something called the diffusion equation, and that's what I'm going to be talking about now. So I will introduce the diffusion equation with this weak flow assumption, and then show you what that means physically. And to complete this diagram, you can go from the scattering equation that Miles came up with and assume spatial scale separation, and that takes you to the diffusion equation as well. So that's the stuff on the Wigner transform. The rest of the talk isn't too concerned with it. Does anyone have any questions on that now before I move on? If not,
because the Wigner transform is a nonlinear function. It's phi or like.
Yes.
The transform would be linear.
I don't think so. No, I don't think so. So to do the actual transform, you take the time derivative of the Wigner transform, and then you sub in your equations of motion using the chain rule. So you have a time derivative of phi and a time derivative of the conjugate of phi. So you do get nonlinear terms appearing. I guess you deal with that when you're doing a perturbation expansion of it in small parameters.
Always combine this with an asymptotic expansion.
I'm not sure, sorry.
Was it really used in time series analysis?
I'm not let me think. So
here they always use epsilons and
yeah. Yeah, I guess, I mean, I don't think we'd have to combine it with perturbation theory, but whether you actually get anything meaningful is, so you can take the Wigner transform and then you have a result, whether that is a meaningful result without taking perturbation theory, I'm not entirely sure. Hopefully something we can get to the bottom of for the next couple of months. Yeah. Anything else? No? We can talk more about it later because it is confusing to me anyway. So yeah, we're gonna now talk about going from the action conservation equation for inertia-gravity waves to the diffusion equation. So this is something that I think you'll be more familiar with than me. In a rotating stratified fluid, you have a coexistence of inertia-gravity waves and a geostrophic flow. The inertia-gravity waves have this dispersion relation. F is your Coriolis frequency, theta is the polar angle from the vertical, and n is your buoyancy frequency. The waves propagate in the regime we're considering a lot quicker and on shorter spatial scales than the geostrophic flow. So the geostrophic flow, because the waves are propagating the time dependence of the waves is much more than the flow. We can take the flow's frequency to be approximately constant, zero, and I'll relax that later. So one thing we should note now is because the frequency of the waves is only dependent on the polar angle theta, in wave vector space, the constant frequency surfaces are going to be a cone where theta is constant, and that will come up later. So why do we care about inertia-gravity waves and their interaction with the geostrophic flow? Okay, this is observational oceanography now, so it's really not my strong point. But this is an atmospheric energy spectrum taken from a paper by Callias, Ferrari, and Boussinesq. For the larger scales, the geostrophic flow is dominating this total energy. So the total energy is your black line, the geostrophic flow is the red line, and the inertia-gravity waves are the blue line. For the larger scales, the geostrophic flow is dominant, but as you move to smaller scales, the inertia-gravity wave component begins to dominate. There's also some mechanism in the ocean transferring energy from larger scales to smaller scales. It's not the flow because the flow is 2D turbulence, and it's postulated that this is the waves. So we care about how the waves are interacting with the flow, and we care about what their energy spectrum looks like. When they interact, this is a scattering process. So this is I'm gonna show you a full Boussinesq simulation. On the left, we've got basically the vertical vorticity of the flow. And on the right, I think it's a bit more complicated than just the vertical velocity, but it's basically the wave signature. So we have a fully evolved Boussinesq flow and we inject a wave into that flow. And this was the scattering equation that I showed you in the bottom left of the previous diagram. And as you can see, when you inject this wave into the flow, the wave loses its wavelength, it loses its preferred direction, and it isotropizes, so it scatters. And the flow remains fairly consistent throughout. The length scales don't really change. It has no preferred direction at the start to finish. So it's like a catalytic interaction between the waves and the flow. And the maths behind this is summarized in that paper that I showed you earlier. So as I showed from this diagram, one regime of this scattering equation is the diffusion equation. And you can also go from the action conservation equation to get the diffusion equation. So I'm going to be talking about this diffusion limit and going from the action conservation to the diffusion equation. So our starting point is the action conservation equation. A is your wave action, that's just proportional to your wave energy. So if you solve to find wave action, you can make predictions on the wave energy distribution. It's a function, as we just talked about, in physical space and wave vector space. So you have something that's changing in both. Omega is the total frequency of your waves. So it consists of an intrinsic frequency part. This is the waves propagating without flow. And then here we consider a Doppler shift term. So this is the impact of the flow on the waves. And I think that's what you need to see there. We're going to make a few assumptions on this equation to allow us to simplify it with asymptotics. So we're going to first assume that the flow is very weak. And in reality, what that means is we put a bookkeeper parameter epsilon in front of this Doppler shift term, which is very small. This is just the Rossby number, which is small in our regime. So this weak flow assumption allows us to expand the action conservation equation asymptotically. We make a further assumption that the flow is time independent. I'll show you the full ramifications of this in a minute, and I'll relax this later. And then we also make an assumption that the flow is homogeneous, random, and statistically stationary. And this allows us to do some averaging over higher order terms and get rid of them. So these assumptions allow us to do some asymptotics. I'm going to miss that out because it's fairly tedious and just give you the result. So this is our diffusion equation. So the left-hand side is some advection term with C, which is the group velocity of the waves. And the right-hand side is our diffusivity. So if you've seen diffusion equations before, you're probably more used to a one-dimensional diffusion. Here we have a tensor D, which is a 3x3 tensor. And what that means is you can have gradients of action in one direction driving changes in action in the other. So usually in diffusion, you have a gradient in one direction that drives a change in the same direction, whereas you can have cross terms in this diffusion tensor. That's not actually what we get in reality, but it just allows for different directions of diffusion. This diffusion tensor, again, I've not shown the full form of it because it's not massively relevant, but the important part is that it's dependent on the flow rather than the waves. Well, it's also dependent on the wave vector, but it's dependent on the flow. And because of the assumption of flow time independence that we made before, because the flow is going so slowly and we've assumed that it's time independent relative to the quick moving waves, this diffusivity tensor is actually orthogonal to the polar angle unit vector. So what does this mean in reality? It means that there's no diffusion in the polar angle direction, which means that there's no diffusion across the cones of constant frequency. And this diffusion equation, it was first derived by Thomas and Bretherton in 1977. The asymptotic derivation is in the following paper by Cafe Badsava and Vernest. So do we see this in reality? So the same Boussinesq simulation I showed you before of the waves being scattered by the flow, that's just snapshots from it on the top in the physical space, and in the wave vector space, that's what we see on the bottom. So you start off with energy distributed at a single point in wave vector space corresponding to a single wave vector for the plane wave. As energy is scattered, this energy, as the wave is scattered, this energy begins to diffuse, and it diffuses along the cone of constant frequency. So you'll see that most of the diffusion happens along the cone rather than across the cone. So this is in agreement with the prediction that there's no diffusion across the cone of constant frequency, and it's a pretty good agreement. So the summary so far, we've got rotating stratified fluids characterized by gravity waves and geostrophic flow. The flow is scattering the waves, and in the limit of weak flow, we have a diffusion equation which predicts that there's no diffusion across the cone of constant frequency when we assume that the flow is time independent. So what's the problem? Well, there's this paper by Oliver Bouhler's group that considers diffusion for the shallow water system. So in the shallow water system, it's two-dimensional rather than three-dimensional. And what they do is they introduce slow time dependence into the flow. So whereas the previous paper assumed that the flow was so slow it was time independent, they introduce a small amount of time dependence. And what this leads to is actually significant diffusion across the constant frequency cone. So what you're seeing here is ray tracing simulations in 2 dimensions. So because it's 2-dimensional now, we're basically taking slices of the cone. The constant frequency surface is a circle rather than a cone. So you can see, and this is just, 2 wave numbers. You can see that so alpha quantifies how time dependent the flow is, basically. And for no time dependence, it sticks pretty well to the ring of constant frequency. As you introduce time dependence, the rays move further and further away from the ring, which is contrary to what we found in the 3-dimensional case where they stuck to the cone. So is this what we see in 3D? Well, this is a forced Boussinesq simulation. So before I showed you an initial value problem of a wave injected into the flow, this is a forced system, so you have some forcing, and it's the steady state solution at a long time. The vertical axis is your vertical wave number, and the horizontal axis is your horizontal wave number. And so it's basically taking vertical slices of the cone. So the cone are these dotted lines here. The forcing is at 2 single points on the cone, so it's forcing at the top and the bottom of the cone. And the darker areas indicate higher energy and the lighter areas indicate lower energy. So you can see that at the forcing points and along the cone, energy is more concentrated, but there is diffusion across this dotted line. There is diffusion across the cone of constant frequency. So what we set about to do was quantify this diffusion. we asked the question, can flow time dependence radically alter the diffusion of inertia-gravity waves by geostrophic turbulence? So to do this, we're going to make the flow in the system time dependent. We're going to consider the four steady state system that I've just shown you for simplicity.
In Miles' paper,
Yeah.
there was also time dependent of the flow.
Uh,
Time dependence.
Yes, yeah. So we assume that, so in Miles's paper on the diffusion equation, when you're doing the asymptotics, you have your quick time and your slow time. And in that, he has that the flow is only dependent on the slow time. So to leading order, it has no time dependence. Whereas for us, we introduce quick time dependence to the flow. So where there's a big T in his paper, ours is a little t. So that's the difference between.
It's realistic that geostrophic flows slowly evolving.
How do you mean? So that is it realistic that it's slowly evolving?
No, question is it realistic that it's fast? It's not fast, it's slow. But it's
No. So we still consider that it's slow. We have a small parameter in front of our, but it's not as slow as it was in Miles's paper. So in Miles's paper, it was so slow that at some point you just completely lose the time dependence. We retain a little bit of that time dependence and see the effect. So it's somewhere between very slow, and not slow. We're at the slow point, but not the slow point.
Does it have anything to do with this epsilon?
Sorry?
Does it have anything to do with this epsilon?
It does, yeah. So I'll say that again, sorry?
Show the fastness or slowness using this.
Yes, yeah. Yeah, I guess it's kind of it's like in Miles's paper, what he does is you have the slow time dependence is equal to epsilon squared times the times the quick time dependence. And for us, we have quick time dependence, and then after that, we then say that it's slow. So it's not in the same. Do you see what? Okay. Yeah, maybe I can show you afterwards work. But we basically take the fact that it's slow later on in the derivation. Yeah, so we're going to be making it time dependent. It has the same time dependence as the waves to start off with, but then we're going to say that that's slow. We're going to consider the system I just showed you, and we're going to solve the diffusion equation. So it's a boundary layer in wave vector space. It's not in physical space. And this boundary layer is close to the cone. And we're going to try and find an energy distribution close to the cone. And if this energy distribution decays within a small boundary layer, then we're in business because that means it's localized. But if it persists, then that raises the issue of flow time dependence being significant. So this diffusivity is dependent on the flow, which means that this now has time dependence. We get rid of this assumption of flow time dependence. And immediately what that means is the diffusivity tensor is no longer orthogonal to theta, which means that from the off, you see that there is diffusion across this cone. And that's what I want to quantify. So we're going to be finding a correction to the diffusivity using the fact that the flow time dependence is slow. So you have the diffusivity, it has quick time dependence in, and then you impose this epsilon, which is a ratio between the flow frequency and the wave frequency. In the previous bit where there was very slow time dependence, this epsilon was 0 because the flow frequency was approximately 0. In our case, it's very, very small. It's a ratio between the flow frequency and the wave frequency. For realistic turbulence flows, it's basically the same epsilon that you saw before, which was the Rossby number. So yeah, we have very small flow time dependence. Once we've found that correction, we're going to solve the corresponding PDE for energy, which is proportional to action. We make some simplifications. We assume the wave statistics are independent of the horizontal. We don't really care what's happening diffusing around the cone because energy will diffuse around the cone in the steady state solution and then it will stop diffusing. So we're not that bothered by that. We're going to consider, so I probably should, so this diffusion equation at the top here, this is your steady state force equation. So you no longer have an advection term and you have this forcing F. And we consider forcing in a ring. So it's at a constant wave number K, radial wave number, which puts you a point on the cone, and then a constant at a certain radius, and then a constant theta, which fixes you on the cone. And we force horizontally in a ring. And the solving in the boundary layer that I just talked about, that's mathematically means this. So we transform our angle variable from theta to theta star, which is our forcing angle, plus epsilon, which is our small variable, times sigma, which is our rescaled angle. So we're going to find a solution in terms of sigma, our rescaled angle. And if the solution decays with sigma, then it means that you have something decaying rapidly in sigma, which means it's decaying even more rapidly in theta, which means it's very local to the cone. I'm going to skip again all the maths there, but you end up with something which is quite nice. So this is our energy spectrum in radial wave number K and rescaled angle sigma. And this probably won't mean too much for you. Q is the Legendre function of the second kind, which, unless you know your special functions very well, won't mean anything. So I'll show you some plots. This is the E. Oh, this is the E that you can see up there, plotted. It's rescaled to make it non-dimensional. So we're plotting energy against rescaled angle for different values of the radial wave number. And what this basically means is sigma equals 0 corresponds to theta equals theta star. So that means you're sitting on the cone. And as sigma increases, you're moving away from the cone. So the energy distribution is peaks on the cone of forcing frequency and decays rapidly away from the cone. In fact, it's very rapid. The power law is something like sigma to the -5. So it's a really rapid decay. And all of this takes place inside a boundary layer, which is very small already. So we have really high localization to the cone. And we can conclude from this that flow time dependence does not radically alter the mechanism of waves being diffused by geostrophic turbulence. We've compared this to the Boussinesq simulation I showed you. So the fourth Boussinesq simulation, this is the equivalent wave energy plots from that. So what we've done here, we have two parameters. We have a parameter which is the thickness of the layer, the boundary layer, and the strength of the forcing. And we fitted our exact solution to the two parameters at the top here, and then use the same two parameters for each value of the wave number. And you can see that these two parameters that we get in the first one roughly capture both the magnitude and the rate of decay of the energy distribution. So there's good agreement with the Boussinesq simulation as well.
If you're on the left side.
Yeah, so the fact that it's on the left is, so there's a couple of reasons why that might be. One of them is when we're working with this angle, it's a very small angle, so you're very close to F, but it means that in the grids of the whole simulation, you're only covering like a couple of points for when you're very close to theta equals 0. So when you're very close to that point, you've only got a few grid points, and then it's as you move further away, you have more grid points. So I think that's part of the reason it shifted. To use a vague term, it would be like edge effects, basically, because you're quite close to the edge of the domain of the simulation. Yeah. So this is some observational oceanography again. I'd be interested to talk to anyone about this, actually. So we've been thinking recently that, so there is broadening of the energy spectrum because of the time dependence of the flow. We have, from our method, a way of quantifying this broadening. It's the boundary layer width. It's roughly how time dependent the flow is. And we've been thinking about whether from mooring data, so this is just a paper by Lueck et al. It's Brian Arbig's group. We're not too concerned with the contents of the paper, it's just a wave energy spectrum. So they're comparing it to different models. We're really concerned with this mooring data here, the black line. The far left line is your diurnal peak, then the dotted line is your Coriolis frequency, and the peak that is most prominent is your semi-diurnal peak. And you'll see that this peak is broadened, and we're gonna have a go, it's a bit of a long shot, and see if the broadening of this peak is because of the time dependence of the flow. So we have an expression for how thick this peak is from our asymptotics, and we want to look at whether this is the same, you know, if there's a correlation between this and the actual thickness from the mooring data. I'd be
forcing on the half daily. But you assume that the forcing is on that peak.
yes, yeah.
That's the second problem.
Sorry?
Okay.
Okay. Yeah, so I mean, basically the ideal situation is we'd have the thickness we predict and the thickness you can measure, which isn't untrivial because there's not too many mooring points around here. And how do you determine the thickness of this peak? Where do you just say the peak ends? That sort of thing. These are all questions I would like to talk about if people have any more ideas about wave energy spectrums than I do. Also just where to get mooring data from that is good. I just found a paper with mooring data, and if you guys have any more advice about where to find mooring data with good peaks, that would be very nice. Yeah, so as people who deal with that sort of thing more often, let me know. Yeah, it's unlikely that this is the reason, but it would be nice to see if it does contribute to the widening of the peak. And I believe that if you do see a peak widening, that is because of the presence of the flow. But again, I don't really know anything about that sort of thing. So yeah, please talk to me about that. So a summary, ignoring the Wigner stuff, you can model the inertia-gravity-wave and geostrophic flow interactions in diffusion equation process. And with time-independent flow, you predict a very localized energy spectrum. Relaxing the time independence of the flow results in an energy spectrum that does diffuse across the cone, but it's very, very localized. And this energy spectrum is in good agreement with the Boussinesq simulation. And yeah, if you want to talk about the Wigner transform, internal tides interacting with eddies, this diffusion stuff, generalizing this diffusion stuff to other perturbations or mooring data, I'm here for 2 months. So please let me know if there's anything you can enlighten me on. Yeah, so thanks for listening, and yeah.
Someone.